In this video, we will look at how to implement the Minimise Detours example in Mobius. In the Minimise Detours example, the positions on a set of lines are attracted towards each other, creating a clumping effect. One possible application is the generation of a set of paths connecting points of interest in an urban environment. In this example, an urban massing is generated based on the paths, as a simple demonstration of this idea. The flowchart has 4 parameters. The first is a random seed for generating the initial lines. The second is the maximum distance of attraction between positions. The third is the damping factor that reduces the amount each position moves. The fourth is the number of iterations. Next, we will focus on the code in the solver node. The task of the solver is to move positions towards one another. To do this, the solver iterates many times, each time calculating new coordinates for the positions. To get the correct clumping behavior, the coordinates need to be updated gradually, in many small steps. The solver has 4 main steps. The first 2 steps are preparing the data for the solving process. In step 1, the positions are extracted from eth polylines. And in step 2, a map is created that links each position back to the polyline it belongs to. This map will be used later when finding the neighbors of positions. The third step is the main body of the iterative solving process. Based on a list of existing coordinates, a new set of coordinates is calculated. This step gets repeated numerous times. Each time round the loop, the new coordinates become the input for the next iteration. Finally, in the fourth step, the positions get moved. Note that in step 3, the coordinates get updated, but the positions do not get moved. The positions only get moved after the whole iterative process is completed. Repeatedly moving the positions after each iteration would be much slower. Step 3 loops over all the positions, and applies 3 sub-steps. First, if the position is in the list of fixed positions, then the new coordinate is set to be the same as the old coordinate. Second, if it is not fixed, then a set of neighbors are found based on a threshold distance. Third, based on the coordinates of the neighbors, a new coordinate is calculated for the position. Let's look at the code for these steps. The first step focuses on extracting the data needed for the solver. 2 lists are generated in the process. One list is all the XYZ coordinates of the positions. The other list is the indexes of all the positions that are fixed, and that should therefore not be moved. At the same time as extracting this data, an additional attribute is also added to each position. This attribute specifies the index of the position. This index is required in the next step. The second step focuses on extracting information about the relationship between positions and lines. Later, each position will need to find all its neighbors. These neighbors must exclude positions that are part of the same polyline. Some data is therefore needed that can be used to check which polyline a position belongs to. For this, a list is created that maps from the position index to the polyline index. We call this the positions to polylines map. The third step is the main solver loop. This step is broken down into a number of sub-steps. First, notice that the solver has 2 nested for each loops. The outer for each loops over the iterations, the inner for each loops over the positions. So for each iteration, the solver processes each position. Before starting the inner loop, a temporary variable is created for storing all the new XYZ positions that will be calculated. Initially, the variable is an empty list. The inner loop will gradually fill the list with the XYZ coordinates of all the modified positions. After the inner loop has completed, the modified XYZ coordinates are saved back to the main variable. Inside the body of the solver loop, The first step is to check if the position being processed is a fixed position. The endpoints of the polylines are fixed positions. They should not move. If it is a fixed position, then the XYZ coordinates of the position are simply copied without any modification. The continue statement then forces the loop to continue onto the next position. The next set of statements inside the body of the solver loop then get the neighboring positions. The neighbors will be those positions that are closer than the threshold distance specified in the flowchart parameters. This uses a local function that we will have a look in a moment. But for now, you can assume that this function returns a list of indexes of all the neighbors. The position being modified will be attracted to these neighbors. The last set of statements inside the body of the solver loop create the modified XYZ coordinates. For each neighbor, a force vector is created. The magnitude of the force vector is inversely proportional to the distance to the neighbor. So neighbors that are close exert a greater attractive force than those that are further away. The damping factor is also applied, thereby ensuring that the movement of the positions is not excessive. The force vectors for all the neighbors are added up, creating a final cumulative force vector. This vector is then used to generate modified XYZ coordinates of the position. These coordinates are saved in the temporary list. The fourth step is executed after the iterative loop in step 3 has completed. In this step, the modified XYZ coordinates are used to update the position entities in the geometric model. Now we can come back to the local .getNeighbors function. The function loops through the coordinates of all positions to find those that are neighbors. The function has 3 arguments. The first argument is the index of the position being modified. The second argument is the list of coordinates of all the positions. And the third argument is the positions to polylines map. In the body of the function, there is a for each loop that loops over all position coordinates. There are 2 indexes, called I and j. Index I is for the target position. That is the position whose coordinates are being modified. Index j is for the potential neighbor position. If the potential neighbor position is part of the same polyline as the target position, then it is skipped by calling continue. If not, then the potential neighbors is accepted or rejected based on distance. Calculating the Euclidean distance to all position can be quite costly. An additional step is therefore added to first check the 2D distance. If the 2D distance is less than the distance threshold, only then is the Euclidean distance calculated. Next, let's have a look at what this code produces as results. Here we can see some of the results from executing the solver for varying numbers of iterations. As the number of iterations increases, we can see the positions moving closer together. Another way of modifying the output is to increase the threshold distance. A third modification could be to adjust the damping factor. As a simple illustration, a set of plots and building massings have been generated from the paths